Atom stability. Certain atoms are stable and therefore they do not react chemically. And many other atoms are unstable and therefore are going to react chemically. So what determines whether or not an atom is stable? It has to do with the number of valence electrons. Remember when we learned about the structure of the atom, every part of that atom had a specific job. And the specific job or importance of the electron was to determine how an atom reacts chemically. And for atoms, it's specifically those valence electrons, the number of electrons in the outermost shell, or the highest occupied energy level. So for an atom with 8 valence electrons, it's going to be stable, which means that atom is not going to react chemically. Those things that do not react chemically, we call those inert substances. They're unreactive. Those things that do not react chemically, they're known as inert substances, meaning that they are unreactive. And as we're going to see later on in the course, these atoms do not bond with other atoms. On the flip side, you're going to have unstable atoms. How do you know if it's unstable? The outer shell is not full. It does not have 8 valence electrons. So because of this unstable nature of this atom, it's going to react chemically. And therefore, it is going to be found in molecules and compounds, and because it's going to bond to other atoms. There's one big exception to this general rule of 8, which we refer to as the octet rule, oct meaning 8. There's only one atom that is going to, or actually 2, that can be stable with less than 8 valence electrons, and that's your hydrogen and helium. Because they only have 1 occupied energy level, there's the maximum number of electrons that can fit in that first energy level for hydrogen and helium is 2. So hydrogen and helium are full when they have 2 electrons. So just make yourself a note of that. One exception to this rule of 8 valence electrons, because hydrogen and helium are on the first row of that periodic table, they only need 2 valence electrons to fill that first energy level. Now, what does this look like in terms of electron configuration? Let's consider the atom fluorine. Let's write out the electron configuration for fluorine. So let's turn to our periodic table. Let's locate fluorine on the periodic table. Fluorine is right here, number 9. So assuming we have a neutral atom of fluorine, it's going to have 9 protons and 9 electrons. So we want to write the electron configuration containing 9 electrons. So as always, we start with hydrogen, and we're going to end with fluorine here. So the electron configuration would be 1s2, 2s2, and 2p, 1, 2, 3, 4, 5 for fluorine. If you need a refresher of how to write electron configurations, please watch the videos provided in this assignment, or refer back to your notes from previous lessons. All right, so I have the electron configuration of fluorine. Let's draw out the orbital notation as well. 1 box for 1s, 1 box for 2s, 3 boxes for 2p. And we go in and fill in our electrons. 1 up, 1 down, 1 up, 1 down, and very close attention here to 2p. Up, 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 down, down. If you need a refresher of how to draw orbital diagrams or orbital notations, please refer back to your notes and previous video lessons. Now, is fluorine a stable atom? Look at the electron configuration. Let's determine the number of valence electrons present in an atom of fluorine. Locate the highest occupied energy level. So that means look at the coefficients. The largest coefficient is the number 2. So look at the number of electrons located in that second energy level. You're going to have 2 inside of 2s, and you're going to have 5 inside of 2p. So the number of valence electrons, you're going to add those exponents together. So 2 plus 5 equals 7 valence electrons based off of that electron configuration. You can also use the orbital notation to determine the number of valence electrons as well. We do the same thing. We look for the biggest coefficient, and that is a coefficient of 2. And this one, you're going to literally count the number of arrows present. You got 1, 2 inside of 2s, and you have a total of 5 inside of 2p. So if you're counting the arrows, count the arrows inside of 2p and 2s, you're going to get 7 valence electrons. So either way works for determining the number of valence electrons. So the question is fluorine stable or unstable? Well, the magic number, remember, is 8 valence electrons. And so with 7 valence electrons, fluorine is unstable because it has 7 valence electrons. Or you could say because it doesn't have 8 valence electrons. So fluorine, being unstable, is going to react chemically with other atoms, meaning it's going to make bonds. And as we're going to see, fluorine, when it makes bonds, it typically is going to gain 1 more electron through a chemical reaction by making a chemical bond. And take a look at that orbital diagram. Why is it going to gain 1 more electron by reacting chemically with another atom? Looking at the orbital notation, the second energy level is almost full. It almost has 8 valence electrons. The S is full, but the P is not quite full. Look what it's missing. It's missing 1 electron in this last orbital of 2p. It has a total of 7 valence electrons. It's just 1 electron away from having 8 valence electrons and becoming stable. That's the ultimate goal of these atoms. That's the whole reason why atoms bond. It's to become stable. And to become stable, they have to fulfill that octet rule. They have to fill that highest occupied energy level with 8 valence electrons. So what's fluorine going to do? Fluorine is going to try to steal an electron from another atom. And that's exactly what it does. Fluorine is highly reactive. It's just 1 valence electron away from having its 8 valence and being stable. So it's going to snag an electron from another atom somewhere. And so when it snags another electron, meaning when it steals or when it gains that 1 electron, what is its electron configuration going to look like? Remember, it starts with this orbital notation. Just needs to fill in one more electron into that last 2p orbital. So imagine an electron coming over and being added right there. Let's go ahead and highlight that. That last down arrow represents that electron that fluorine has now gained. And you can see here now, look, the 2p is entirely filled. That's a good thing. And count with me. Now, how many valence electrons does the fluorine have? Highest coefficient is still 2. You have 2 electrons in 2s. You have now 6 electrons in 2p. So we now have 8 valence electrons after fluorine has gained 1 electron. Now, fluorine is stable with its 8 valence electrons. What's the electron configuration? Well, remember, this is how it started. It started as 1s2, 2s2, 2p5. But didn't we just gain 1 electron? Didn't we just see in our orbital notation that we just added an electron to 2p? So now count how many electrons are inside of 2p. We're going to have to change that exponent on 2p to 2p6. This electron configuration now matches what we have in our orbital notation. And you can double check yourself. How many valence electrons are in this electron configuration? We have 8 valence electrons. So fluorine can become stable by gaining 1 electron. And it's gaining 1 electron so it can have its 8 valence electrons. But there's something we have to change in terms of the symbol of fluorine. This is not neutral fluorine anymore, guys. Fluorine now has an extra electron. It now has 10 electrons. So the symbol for fluorine is not just F anymore, but it's F1 minus. That 1 minus tells us it has gained 1 electron. And you can double check yourself. We know that fluorine is number 9 on the periodic table. So that means 9 protons. But a 1 minus means, hey, there's 1 extra electron. There are 10 electrons in the fluoride 1 minus. And so what we have here on our paper is the orbital notation for fluoride 1 minus ion and the electron configuration for the fluoride 1 minus ion, because that is the result of the fluorine atom gaining 1 electron.